After many dark matter models, and one of the types of dark matters is the thermal dark matters, which is produced by the uh, thermal equilibrium. And today I will talk about some of the one papers that are the journal club with instead of the WIMP dark matter. In the archive number is 2003 April 00908 in the PRD is published in PRD. So the in the user dark matter, especially the thermal dark matter, there are two different scenarios. The first one is a WIMP result. So the if the coupling is the weakly interactive strength, or the lambda is given by the one of the 10 or 0.1 scale, there's such a WIMP dark matters that breathes out of the equilibriums or decoupling. So the in this case, the dark matter chi and its on-tip particles annihilate the standard model particle FFR. But if the interrupted couplings strength is extremely small, like the Beeble strength, is called the FIMP, Beeble interacting mass particle. Lambda is given by the almost 10 to the minus 10 in this case. Because of the very Beeble interactions, such a FIMP dark matters cannot reach the equilibrium density, unlike the WIMP dark matter. So it should be produced by the inverse process of the such annihilation. So that there are paired creation process of the WIMP dark matters appears, and that is called the within WIMP dark matter. And actually, both the WIMP and the WIMP scenario should be the bit with the observed dark matter density value. Omega h is case equal to 0.1. So such a behavior of the beam breeze in and the wind breeze out shown in this figure. The possible the WIMP dark matter case, the density is reaches the equilibrium, thermal equilibrium. But if the temperatures are cooled, so it becomes less than the mass, then the production lies get the Boltzmann approaches the boxes. So the WIMP dark matters are decoupled at the moment, where the variables are given by the m over t, and it becomes fixed for such a moving number density. So it's a bit for such observed value. And then we can find such a behavior of the following the thermal equilibrium and the decoupling moment and the binary moving abundance by solving the Boltzmann equation. So first of all, such a breeze-up moment can be obtained by the comparison between the production light and the Hubble's expansions light, and the behavior of such a moving number density can be obtained by solving the Boltzmann equations given like that, so with the annihilations cross sections, and there are some of the how such a number density is the bar from the equilibrium density, and then we can obtain the binary abundance by integrating of such Boltzmann equations from the initial point to the breeze out moment. Similarly, we can analyze the similar behavior for the BIMP. So we can solve the Boltzmann equation for such a BIMP dark matter, but the different thing is the density that does not reach the equilibrium, thermal equilibrium. So it produces the dark matter produced, and it becomes the same with the observed values of the dark matter abundance. And the one thing I want to mention is that it looks like very similar with the strong washout in the leptogenesis, and this is the same dark matters that has a similar behaviors with the weak washout because of the very small coupling. And we can also make the breathing of the WIMP, which is the topic of this paper. So they used some of the super cooled burst order phase transition. So there are some of the FOPT phase transitions temperature moment T2, and we can parameterize the T2 as m over the T2. And such a burst of the page transitions mean that there are latent heat when such as some of the build value that transits from the burst vacuum to the tube vacuum. And because this is a burst of the page transition, the two pages, the burst vacuum and the tube vacuums, can be existed simultaneously. So the bubbles that created at the tube vacuums and such a tube vacuums bubbles are expanded. So it is called the burst page transition. And how does such a burst of the page transition can realize that there's such a breeze in of the WIMP? So it still means that the coupling has a weakly interactive strength, but the dark matters density does not reach in the initial conditions, and because of such a low density, so the dark matters are produced. So even the couplings that weakly interrupt trans, there's such a WIMP dark matters that breathes in under such a supercooled burst of the page transition. And first of all, before the page transitions, the dark matter sky does not have the mass, is a massless, because by absolute such as color field pies is equal to 0 before the page transitions. And after the page transition, the color field pi get the bulb, so the dark matter becomes a massive. So the before the such a page transitions, the such a variable z equal to 0. But after the page transition, now can the Boltzmann equations can be operated, so the evolutions of the number densities are started. And because of such a massive dark matter, so the Boltzmann suppression factors are multiplied for the production light, so that it prevents the thermalization. Before that, there's such a page transition because of the massless dark matter, such a Boltzmann suppression factors and evolution behaviors and number densities that doesn't appear. And the second thing is how such a supercooled page transition can help. Because during the page transitions, the energies are released, the latent heat, when the transition from the Bose vacuum to the vacuum, and also the entropy densities are increased. So there's such a common number density, which is defined as the number density of the entropy densities that becomes diluted because of the large denominator. So how does realize such a model? And before that, they are analyze some of the model independence approach. How this each scenarios can beat the dark matter's abundance, and they assume that the dark matter's chi is produced by the scalar boson scalar speed b. So there are some chaotic coupling between the two scalar field b and the dark matter b chi with the coupling lambda. So the first of all, the observed values is the omega chi h square dark matter abundance is the 0.12, and this can be calculated by the definitions. Omega is the ratio of the dark matter densities over the some of the critical density, and the energy densities are given by the multiplications of the mass and number density of dark matter. And by using the definitions of the commuting abundance, so we can obtain the relation between the observed values and the results of the solving the Boltzmann equation. So after the solving of the Boltzmann equations, by using the adopting the such interaction, so in the result case, the two dark matters annihilate to the two standard model particle, ordinary particle. And by using the such a annihilation cross action, we can solve the Boltzmann equation numerically. Then the such dark matter abundance can be based with some specific parameter, possible coupling lambda, and the dark matter mass. So if the typical dark matter mass is given by the Teller electron volt, and the coupling is 0.1 to beat the 0.1 dark matter abundance. And you can see that the coupling is weak strength, almost 0.1. So the alpha W in the standard model, so weak coupling is almost all about dot, so almost similar. And if the lambda is smaller, then the breeze out occurs a very early time. It means that dark matter abundance becomes increased. And also, if the dark matter mass is large, then because of the earliest Boltzmann suppression factor, so the breeze out earliest occurs, so the dark matter abundance also becomes increased. So, and the second scenario is FIMP breathes in, and in this case, there are no mass dependence. Dark matter's mass does not box the abundance. In this case, the also the solving the multiple equations by using the creations, the cross action. The abundance is given by dust, and the typical case of the coupling is a 10 to the minus 11, which is very big. When the interaction strength, such a coupling lambda becomes increases, then the breathes in, I mean, the some of the productions becomes enhanced. So the dark matter abundance also the increases. So there are such a behavior. And there are new scenarios, when breathes in case. There are also the dependence on the period transitions temperature, just two. So there are some of the such factors. Similarly, there are their mass dependence, like as a FIMP breathing, and the coupling is given by the also coupling dependence and the temperature dependence here. And they use the I don't know why they are using the such a 10 to minus 11 very small coupling like it's a BIMP, but maybe there are some of the typo or might misunderstand, but I will just keep going on now. If they just go to choose, then the versus the parent transition go to the infinity. So the coupling is the lambdas becomes small. So the WIMP is in, the reduces in the BIMP is in. So this plot show that the three scenarios simultaneously. The number one is WIMP breathes out, and the number two is BIMP breathes in, and the number three is WIMP breathes in. And they realized the model by using the extensions of the additional particles to understand that model, new scalar, new parabions, and dark matter. And the scalar potentials contains the chaotic coupling between the dark matter and Higgs, dark matter and scalar and Higgs. So the dark matters can be produced by the this chaotic coupling. And because of the Coleman-Weinberg's mechanism, the chaotic coupling indices by the loop with the fermion psi. So the potential to get the additional effective term, which is given by the pi 4 times ln pi over the omega. So the scalar pi has the bound with the omega. And if the Higgs get the bulb and the pi get the bulbs, they also the penetrations are realized and the documented pi get the mass. So the supercooled also all the penetrations can be realized through which it triggers that there's such a WIMP breathing scenario.